Hi, I'm Pete Rulon. Today we're going to discuss the section of the Part 107 commercial drone license test that deal with the information on loading and performance for unmanned aircraft. The center of gravity, balance and stability, performance data predictions, and aircraft loading procedures. So, small unmanned aircraft loading, you need to take in consideration weight, stability, load factors, and the weight and balance. So, there are four factors acting on an airplane in flight. They are lift, that's the upward force that holds the aircraft in the air. Weight, that's the force of gravity pulling the aircraft down. Thrust, the force which moves the aircraft through the air. And drag is the aerodynamic friction. So before we start, is the drone loaded properly by determining the weight and balance condition? Review the manufacturer's restrictions and limits in the pilot's operating handbook. Know the effects of specific loading on performance and how much is the loading going to affect your power consumption and how much is it going to weigh when you go to land. If a cargo is attached to the drone, it may shift the center of gravity. Adverse balance conditions, i.e., improper weight distribution, may affect flight characteristics. You must comply with the maximum cargo capacity and assure it's mounted so it does not significantly change the center of gravity. Are you doing anything that adds or sheds weight during flight? What will the effect be? If the manufacturer does not provide specific weight balance data, then you need to apply general principles to determine limits for a given flight. So, example, try and add weight to a drone in a manner that does not adversely affect the center of gravity, CG, location. And the CG is the point the drone would balance if suspended from that point. Question: what is the consequence of operating a drone above its maximum allowable weight? Faster speed, shorter endurance, or increased maneuverability? The correct answer is shorter endurance. To assure the unmanned center of gravity limits are not exceeded, follow the aircraft loading instruction in the Aeronautical Information Manual, the pilot's operating handbook or UAS manual, or aircraft weight and balance handbook. Well, the UAS manual is your best source if it contains information on load and center of gravity.
Now, I want you to remember that the center of gravity is the point at which the aircraft will balance. It's what the aircraft literally moves around. It's that center of gravity there.
Factors that may require a reduction in weight prior to flight include high density altitude operations, lower air pressure and high humidity, which would reduce your lift. What type of launch surface are you taking off from? Is it sloped? Do you have surface wind to deal with when you take off? And obviously, a good practice is to keep your launch area clear of obstacles. So the three major components of density altitude that reduce lift are higher elevation, the air gets thinner, heat thins air, humidity thins air. Excessive weight reduces flight performance in almost every aspect, and it can also compromise structural integrity of the drone. So, what are the effects? Well, it has a reduced rate of climb, it has a lower max altitude, it has shorter flight times, and reduced maneuverability. The drone performance can be decreased due to an increase in the load factor when the aircraft is operated in maneuvers other than straight and level flight. And load is typically expressed in units of gravity. So here's a chart that is in your supplement book, and it's going to be used to look at how does the load factor increase when you're performing certain operations. So if you're doing a 60-degree bank, so 60, the load factor is 2. So now the drone is pulling 2 Gs. So you need to check with the manufacturer what is the max G load permittable for that drone. Another thing that the test spends a lot of time on is aerodynamic stall caused by separated flow. The remote pilot should be mindful of the increased load factor and its possible effects on the aircraft's structural integrity and will increase the stall speed. Every aircraft has a critical angle of attack. At that critical angle, there is no longer lift generated. The prop, which is the lift generating airfoil, will lose lift as the angle is increased. In essence, there is separated flow from the prop, which causes a stall because the prop is not lifting anymore. Drones are operating under 400 feet. Due to the low altitude operating environment, consideration should be given to assure the aircraft control is maintained and the aircraft is not operated outside limits. The lower altitude gives the operator less time to correct an error or try and restore normal flight.
Now, let's you and I take a look at a couple of terms the FAA wants you to know about. First of all, let's take a look at an aircraft wing. Now, if you draw a line here from the trailing edge of the wing up to the leading edge, that line is called the chord line, and it points the direction the wing is pointed. Now, if the wing is going this way, then the wind will be coming from the opposite direction, and they call that the relative wind because it's relative to the wing itself. So if the wing is going this way, then the relative wind will be coming from the opposite direction. Now this angle between the chord line of the wing and the relative wind is called the angle of attack. And they sometimes refer to this angle of attack as an acute angle because it's less than 90 degrees. So this acute angle is called the angle of attack. Now let's you and I take a look at this. First of all, you may be asked, what is this acute angle A here? Well, here is the chord line of the wing and here is the relative wind, and that angle is called the angle of attack. So one of the things you need to know is that this acute angle A is called the angle of attack. Now the angle of attack determines how much lift there will be on the wing. Now let's take a look at a wing of an airplane in flight. Now here's an airplane wing in a wind tunnel with smoke going smoothly over it. And when the air flows smoothly over the wing, it's called laminar flow. Now let's take a look at what happens when you change the angle of attack. As you increase the angle of attack, the lift gets greater. However, there's only lift as long as the air conforms to the surface of the wing. Now, when you get the angle of attack too high, the air can no longer conform to the surface of the wing. Instead of flowing smoothly over the surface of the wing, it separates from the wing and then backfills and burbles and eddies. Lift is destroyed and the aircraft is said to have stalled. The point where you increase the angle of attack any more, the lift is destroyed, is called the critical angle of attack.